Good morning, everybody. My name is Athray Nagesh. I'm speaking for Brian Nazarin.
Chris Argenti.
Shubham Anildas.
And Thomas Palmer.
And this is the product description of the high-top wooden table.
So first, an overview of what we'll be talking about today. We're going to talk a little bit about the product, and we're going to talk about our key characteristics, the assembly process for this product, and then kind of analyze that process. So we are creating this high-top table where we have two major things we're interested in. We want to make sure the tabletop is the same level as other counter surfaces in the kitchen, and we want it to be able to seat 6 people. This table consists of 10 parts in total. So the parts, as you can see them in this picture, are labeled 1 to 10. We have kind of three major parts. We have our vertical legs, which are 1, 4, 5, and 8. We have our support structures, which are 2, 3, 6, 7. We have our tabletop, which is 10. And we create this assembly process using the global coordinate frame here, as seen in the picture, with our Z direction up and down, our X along the length of the table, and our Y along the width of the table. So first, our KC1 is between the top of the table and the bottom of part 3. And this is to ensure that it meets the same height as everything else within the kitchen. And so things that are important for this is the thickness of the table, the thickness of the upper stretchers, and the length of the vertical members. Our second is to make sure that we can fit 6 people. And so that's between members 2 and 6. And we want to be able to have those seats in there, which are about 18 inches in length with a gap of 10 inches between them. We have to make sure that these legs are parallel to accomplish this KC. So our liaison diagram for this, as you can see, shows all of our connections between our parts. And most importantly, our KC1 is between that bottom stretcher 3 and the tabletop. And then our KC2 is between the upper stretchers on the inside.
Reviewing the bill of materials for the table assembly, it is broken up into 10 main components, being the vertical members, the upper stretcher, the bottom stretcher, the central stretcher, number 9, the tabletop, then which are all made of white oak. We then have dowels and screws, which are steel, and wood glue to mate the joining members. The dimensioning process is traditional woodworking mill work where we remove material to get the final dimension of each member. And it's at this process where dimensional variation can come into play for each member, which could hurt us in achieving our KCs. We then use our fixtures to catch any dimensional variation, which will not result in a KC being met. Next slide, please. Assembly sequence 1 has 2 main subassemblies for the legs being rectangular in shape. So you have a left leg assembly and a right leg assembly. The left leg assembly starts by joining the vertical member 1 with member 3 through 2 dowels, 2 holes, and mating glue and clamps. That is then done on the opposite side with 4 and 3, creating a U, and then 2 is brought to that U shape to create a rectangle. Similarly, on the opposite side of the table, members 5, 6, 7, and 8 create a rectangle, and they are connected through the central stretcher, number 9. That full assembly is then brought to the tabletop to complete the table. In reviewing the exploded view, you can see at every mating location, we have 2 dowels. We use glue to join them, and we use 6 1/4-20 screws to screw member 9 into the top, which fastens the full leg assembly to the top. KC1 is defined and achieved through fixtures 1 and fixtures 2. It's at this point, using fixture 1 and 2, where we will catch dimensional variation in the members of the legs that would result in the KC not being met. It's at this point where we can scrap parts and make sure that we achieve KC1. KC2 is met through fixture 3, which is the span through the length of the left subassembly to the right subassembly. Next slide, please.
So this slide shows the assembly sequence 2. Essentially, this sequence will have 3 subassemblies that make up all the individual parts and the tabletop. Next slide, please. So this shows all the 3 major subassemblies. The left subassembly is made up of member 1, 3, and 4. The second subassembly is made of 5, 7, 8, and the third subassembly is made up of 2, 9, and 6. As you can see here, the first two subassemblies basically make up a U shape, and the third subassembly make up an I shape. Next slide, please. The way the exploited view shows basically how each member is attached to the other member. We've been using dowels, 2 dowels for each joint, and to screw in the tabletop to the rest of the table, we use 6 1/4-20 screws. We use fixtures to make sure that our KCs are met. As we've seen before, the U subassemblies and the I subassemblies are already made, and we use fixture 1 to mate the left U leg assembly to the left side of the I subassembly. This is where we can catch the part variation. So if the part variation is not meeting the required KC, we have to throw away or scrap away the entire subassembly compared to the subassembly sequence, assembly sequence 1, where we'd have to only scrap an individual member. Here, you have to scrap an entire subassembly, which is not ideal. Could potentially have issues later down the line. Once all the subassemblies are meeting all the KCs, the final step will be to bring in the tabletop to the rest of the subassembly, and this is done with fixture 2. Next slide, please.
So this is the joint type and constraint analysis. As we can see here, we describe the various constraints imposed on the pieces with either the fixture or the joint type. To briefly go over the joint type, almost every joint except for to the tabletop is done through 2 dowels, which is a peg through hole plus a plate on plate joint. So this introduces a constraint of all 6 degrees of freedom between the adjacent parts. For example, 1 and 3 are fixed with the 2 dowels, and those are completely fixed in XYZ and rotations about XYZ. Focusing specifically on the fixtures, we have each fixture, as mentioned earlier, defining particular KC. So fixture 1 helps define KC1 as well as fixture 2, and fixture 3 defines KC2. So I'll briefly go over one part. Part number 1 is then fitted to fixture 1 and constrained in all 6 degrees of freedom, and then part 3 is brought to that same fixture, but is only constrained in Z and rotations about X and Y. This allows the operator to bring that piece directly to the adjacent piece, attaching it. Moving forward to the datum flow chain. So the datum flow chain is described as shown. We can see how the fixture 1 plays a part in ensuring that KC1 is met, and that fixture 2 is also necessary for this. The delivery chain is highlighted in orange. So this introduces or ensures that bottom stretcher 3, upper stretcher 2, and the tabletop are all at the correct Z heights. Datum flow chain for KC2 introduces the fixture 3, which locks in upper stretcher 2 in all 6 degrees of freedom, and brings upper stretcher 6 to the right X dimension. The central stretcher is located to upper stretcher 2, so if it were to be short or long, we would now be able to catch it and scrap that piece, moving and ensuring the KC2 is met. Within the assembly sequence analysis, we compare both sequence 1 and sequence 2. All in all, we see that with sequence 1, KC1 is very easy to achieve because we have individual components that we can bring into fixture 1, ensuring that the height is met, whereas in sequence 2, we cannot. We have a larger subassembly, the U shape and the I shape as described earlier. Similarly, for KC2, for sequence 1, it is much larger assemblies being brought together, so that's inconvenient, whereas in sequence 2, we have a smaller I-frame subassembly, so that's much easier to handle. Then looking at the locating parts, we have sequence 1, which is significantly easier because these are smaller parts being put together to make the first set of assemblies, whereas in sequence 2, we have larger parts, so it's not as easy. Then testing subassemblies, we know that a rectangular shape is more dimensionally stable versus a U shape, which could be, which is not constrained and has no fixture to define its shape. So all in all, we can show that sequence 1 has a assembly sequence analysis point of 17, whereas sequence 2 is 14.
So in conclusion, a few things. First, we found that these 2 assembly sequences did not result in any KC conflicts, since fixture 1 and 2 both define KC1 independently of fixture 3, which then defines KC2. Another big part, as Athreya mentioned, is that with our assembly sequence 2, we kind of aren't able to control that U shape. And so what might happen is that we have issues achieving KC1, in which case we would have to potentially scrap a whole U shape So all in all, our assembly sequence 1 seemed to have performed better and will result in fewer scrap parts and more likely to achieve our cases successfully. Thank you.
Thank you.
Thank you.